Welcome to today's class. We continue with our studies on Noir, writing circuits in Noir. And this time we'll be looking at how to write zero knowledge proofs. Of course, we begin first of all by defining what zero knowledge proof is, and then looking at the patterns in zero knowledge proof, what you can write, and so on. We had already looked at the definition, but we can just recall that a zero knowledge proof is a technique, a cryptographic technique, where the prover wants to convince the verifier that he or she knows a secret without revealing the secret itself or giving any additional information to the verifier. So by the end of the proof, the verifier is supposed to be convinced that the prover knows the secret, but the verifier is not supposed to know what the secret is. So that is what zero knowledge proof is about. For example, you may want to prove you know some password, or that you are above a certain age without necessarily having to reveal what the password is or what your actual age is. So you may want to prove that you're above 18. So by the end of that proof, the verifier must be convinced that you're above 18, but he should not be able to tell what your exact age is. So that is what we call zero knowledge proof. So that is just those are two examples, but we can say as many examples as we can. The zero knowledge proofs have properties, 3 properties. One of the properties is completeness. And what this means is that supposing the statement is true, then an honest verifier will be convinced by that proof, that legitimate proof. So an honest verifier will be convinced if the statement is true. So he'll be convinced by the legitimate proof. That is what we call completeness. And then we have soundedness. And what this means is that if supposing the statement is false, then no cheating prover can convince a verifier otherwise. So you cannot convince the verifier that the statement is correct when it's false. And then the other property is the zero knowledge. And by zero knowledge, I've already explained, is that the verifier should gain no knowledge beyond the fact that the statement is correct. So the only thing the verifier is supposed to know at the end of the proof is that the statement is true, but nothing else beyond that. So that is what we call zero knowledge. In other words, the verifier gains no knowledge other than the fact that the statement is correct. Okay, so we can also look at common zero knowledge proof patterns. And there are 3 practical patterns that we will focus on. The first one is the set membership proof. The set membership, just as the statement says, is that we want to prove that there is a member of a set something is a member of a set. So you want to prove that a secret value belongs to a known set. For instance, you may want to prove that your country is one approved countries on the list. So there's a list of countries that have been approved for something, and you want to prove that your country is one of them, but you don't want to reveal what your country is or the position your country is on the list. You just want to prove that it's part of the countries on that list. So there is a set membership. So just proving that a certain element is a member of a set without revealing that element or any other element in the set. You don't want to reveal that element, and you don't also want to reveal another element in the set. But you just want to prove that that element is part of that set. Now, the other part that we'll look at is the range proofs. So we want to prove that within a given range, or falls within a given range, between 18 and 60 years, but you don't want to reveal your exact age. So this is what we call the range proof. So you're saying that this secret lies within this range, and this you give two limits within which the secret lies. And then the other category is the password verification. So you may want to prove that you know a password, but you do not want to reveal the password itself. So these are the three categories we will focus on, the one after the other. So what we'll be doing is we'll be focusing on one, then doing some hands-on examples, writing examples in Noir, writing circuits of a given example in Noir, and then running that example. So for instance, we look what a membership proof, write some circuit, look what the range proof, write some circuit, and then password verification, and so on. So that's what we'll be looking at. So to begin, we begin with the membership, set membership proof. So, and I've already said that this is, you want to prove that the secret lies within given set, is a member of the set. So we want to prove that a set is a member, an element is a member of the set. So supposing an example, suppose you have, as I had already given an example of approved countries, suppose there is a list of approved countries, and you want to prove that your country is among the approved countries without wanting to point out what your country is. So that is what we want to do, and I'll give an example of that, of this very as a circuit for this example, where you want to show that your country is one of those on the list. So a set membership proof would enable to prove in zero knowledge that your secret value, e.g., your selected country belongs to the non-public set. So I'll pick 5 approved countries. Then I want to show that mine is one of the 5, but I do not want to show which one is it. So this circuit would check the equality between the secret and each element in the set, then assert that at least one match exists. So what I'm saying is, I have elements. So I give those countries, I give them some values. And then have this secret is also a value. So what the circuit taking is the secret I have chosen uh, exists among the 5 values. The secret I've chosen is one of those 5 values. That's what the circuit wants to check. So this is the circuit. Of course, I'll explain what each of these mean. But you can say I began with the strat inputs, secret country, field, and then these are public. And my country is supposed to be private. So when I begin writing the function, you'll see that the country will be private, but the struts here are public. So the strut have set 0, which is a field, set 1, which is another field, set 2, field, and so on up to set 5. Now set 4, and these are 5. 1, 2, 3, 4, 5. Then now I write my function, which has the inputs. Okay, so this is function let con 0 equal inputs and so on. We have cond 1, cond 2, all the way up to cond 4. Then convert bools to fields. So Boolean will be converted to fields because Noir does not give a direct way of adding Booleans, so it's good you convert to fields. So where there's true, you convert to 1. Where there's false, you convert to 0. And then you can now add those fields, because there's no way you can add Booleans directly in Noir. So let cond 0, if cond 0 is 1, else 0. So what this just means is that if it is true, we give it 1. And if it's false, we give it 0. And that is what it means even for the next sentence, where there's true. So we're just converting Boolean to fields. Where there's true, make it 1. And where there's false, make it 0. So that's just conversion. Then this is now the point where we want to sum. And that is why we're converting to fields. So the sum, you're adding cond 0, which is a field, cond 1, cond 2, all of them. And then this is now where we enforce the secret country to show that it's one of the elements listed. Now, if this sum is not equal to 0, okay, just assert that the sum is not equal to 0. So if the sum is not equal to 0, and then it means that your country is one of the elements listed. But if the sum is 0, then it means it's not one of the elements listed. So I said this file assumes it's part of our project with the, okay, so, okay, this was just part of my notes. Now, so I'll explain this code in detail, but that's what is happening. I've given values to the countries, 0, 1, 0, 1. So we just converted where it's true, we give 1, where it's false, we give 0, and so on. Then we come and sum. And if the sum is not equal to 0, then it's true, your country is one of the listed. Now, I've given some tests. I've added some tests here. Now, so the secret country here is 42. Set 0 is 1, set 2, set 1 is 2, set 2 is 42, set 3 is 4, set 4 is 5. So what this would be doing would be comparing your secret and see whether there is a value among these that matches your secret. If there is, then it means your country is one of these countries. If there is none, then it means your country is one of these. So this test will pass because the secret for 2 is the same as this. So it means when this no project that written checks from the list, it says that your secret value is one of the listed. So it means your country is part of the set. Now, but what we'll be doing is basically we are adding, this is not the same as 42, so I give it 0. This is not the same as 42, give it 0. And this 42, give it 1. Yes, yes. And niko class kidogo. Okay, so we've assigned those values 0, 1, 2, no, 0, where if the value is not the same as the secret, like this one will be 0, this will be 0, this will be 1, this will be 0, 0. So when you add them, you find that the sum will not be equal to 0. So the sum is 1. So in this case, it means that your country is one of these. That is basically what we'd be doing, and that's what we've done here. There's this summation here. There's this summation of this part. That is what this part is doing. So after this summation comes and asserts at this point. Then, so that is this example, then this test passes. This test passes. Let's come to the other test. Again, we do the same thing. The secret country is 99. But if you check, you can see that there's no 99. So you can say this will fail, but let's see how it fails. This is 0, 0, 0, 0, 0. So 0 5 times will be 0. So the sum is 0. So this one does not pass. This one does not pass. So that is how it is. Now, what the use cases for this set membership proof? One, you can use it to prove citizenship from a list of allowed countries. You can prove that you come from one of the countries listed or allowed countries. You can also use it to prove an asset belongs to a whitelist and so on. There are so many things you can prove using this. Now, as we've seen, this code proves without revealing the actual value that a private field secret country is one of the public values. So let me share the code. We look at it, how it works before we explain further. Okay, this is the code. Okay, so to set membership, my code is here. So set membership. This is the code that I've been explaining. Pub, set 0, set 1, set 2, all of them public. Then the summation is at this point. And then after summing, you come and say if the sum was 0 or not equal to 0. So if it's not equal to 0, it's true that your country is one of the ones listed. But if it is 0, then it's not correct. These are the inputs. The only input that was not there is this. But this one is expected to fail. So I had given a different one, but it also expected to fail. But the one I had not explained is where we have several values that are the same, identical. So if we are summing, this would be 1 plus 1, which is 2 plus 0 plus 0 plus 0, and that is 2 because the secret country was 99. So the sum is 2, and 2 is not equal to 0. So again, it means that your country is one of those listed. Okay, so I want us to run the code. So I should come out because it's not this. It's called set membership. Let me just copy here and paste. CD. Okay, so we are there. Then we should enter, we should CD, because my main is inside circuits. So I should CD circuits. CD circuits. Okay. So after that, let's say Nago compile. Okay. Compiled. I may want to test our tests to see if they are correct, if they're testing the main properly. Nago test. That is correct. 3 tests passed. There were 3 tests here, they passed. Now you see, this one should fail. So I've written here should fail. So when I run, it does not give me a warning. So I've removed should fail. Let's see whether it fails. Now go test. Yeah, it fails. So it's these tests are testing the main function properly. So I can return that. I can return should fail because I don't want these warnings. So that it's true that I've accepted it's going to fail. Now go test. Good. The other thing you can do is now go compile. No, this one you already did. Now go execute. And that is done. So now execute, you can see that there is a witness which has been saved. on the target here. Witness has been set target, so you just come to where there is target is here, and you can see the witness called set membership proof dot Johnson. That is witness. It's supposed to be dot .gz. Dot .gz. I think because of the GTIG, no, let me again delete this and see what happens. Delete it. Yeah. Oh, there were several here. So it's now here. This is the witness. Okay, let me again just delete it. Let me just delete this. Seems I had run and there were several targets here. I was looking at the different targets. So looking at different targets. So let me again nagocom execute. Okay, now a target is here and the witness is set membership dot underscore proofs dot just gz. This is the witness. So it has been compiled and stored at that point. So this is our circuit. So you can customize it and make it ready for production and even integration into real world. But it's almost ready. It's almost ready. Just a few things to polish it, and it will be ready for production and real world integration. Okay, so we can continue with our explanation of what happens, what this does, what this circuit does. So I said that I will discuss each of the parts of the circuit. So there's this part of the circuit, and I've said here that secret country is private input. So you can see secret country here. Oh, yes. Okay. It's a field. It's a field, but we don't have pub anywhere. So that means it's a field, but it's private. There's no pub. But this will be public. This set will be public. It's a field, but it's public. This also be public because of the pub and so on. All of these are public apart from what you want to hide. So you want to hide the secret country. You don't want the verifier to know what it is. So you make it secret. The rest can be public. And then set 0 to Z4 are public elements, and I've already said. Okay, so I was explaining that supposing this is 1 and this is 2, this is 3, this is 4, and this is, let me say, 42, and supposing a secret country was also 42, it's going to see which, if 1 equals the secret country, if 1 equals to 42, if 2 equals to 42, if 42 equals to 42. So the one, if 42 equals to 42, then it means 42 is among these sets, and therefore your country is one of them. But if none of them equals to 42, then it means that your country is not one of these. Okay. So I've said here that each index is a Boolean, which means it's true or false. So in the next step, it means we will have to convert the Booleans to fields. Make it, if it says false, we'll make it 0. And if it's true, we'll make it 1, and so on. So that is what is happening at this step. And I'd already explained that the reason as to why we are converting is because Noir does not give us a way of directly adding booleans. So the code converts them first to fields, the values 1 or 0. Then from there, we can comfortably sum them up. So at this point, after conversion, we now summing them up. Supposing it was true that cand 0 was false, that means it is not equal to 42, then this would be 0. If cand 1 is true, is equals to 42, then this would be 1. And if this is false, it's not equal to 0, it will be 0. Now, if it's not equal to 42, it will be 0. If this one will be equal to 42, it will be 1. If this one will be equal to 42, it will be 1. So we have 1 3 times, and that is not equal to 0. When you sum, so it means your country is one of these. So that's true. That is true. It means that on comparing your country's value and the value of the set, it was found that they are equal. So if they're equal, then it's true that they're equal. But then we give it a value of 1, which means true. And where they're not equal, we give it a value of 0, meaning false, and then we sum. And I've said here that if the sum is 1, that is, there's only one country or one set that matches the value of your secret country. That is what it means. If the sum is 1, it means there is only one set that matches your secret value. And if the sum is 0, it means there's none that matches your secret value. And if the sum is greater than 1, it means there were more than one values that matched your value. More than one value that matched your value. That is a case where we had set to 0 being 42, set to 1 being 42, for instance. and so on. So where there are several countries, sets that have the same value as your secret value. Then you sum up. So for your country to qualify, it means the sum should be 1 or the sum should be bigger than 1. So it's either 1 or more than 1. But if the sum is 0, it means your country is not one of the listed countries. Now we have, then we have the tests. I had already explained how these tests work. So they're just using what you've already explained, summation. And in this case, you can see that your secret value is 42, and it matches this. So this is true. It's true. So therefore, convert true to 1. This one does not match 42, so it's false. Therefore, give 0. This is also false. This is also false. This is also false. Then we sum this. When you sum this, you get 1. The sum is not equal to 0. So that means, therefore, your country is one of these listed. Of course, it's this. It's one of those listed. So this is just the explanation I've already given. I've said your secret country has been given for 2, and for 2 matches set 2. And therefore, count 2 is true. And this true is converted to a field, becomes 1. All other values, as I had already explained, would be zeros. So when you do the summation, you get 1, and your sum is not equal to 0, which means the test passes. It means that test has passed. And this test is just, we are testing. Tests normally are meant to test the main function. If the main function, the assertion, the main function is correct. Again, these are the example. Your secret value is 77. You can see this does not match 77. This one does not match 77. That means it will be false. Give it a 0. This does not match, will again be another 0. This does not match, does not match, does not match. So those are zeros. So when we sum them, we'll get 0. The sum will be 0. So if the sum is 0, then it means that your country is not one of those listed here. Okay. So this is the explanation. I'll just try to explain. The secret country has been given 77, and then there's no set among the ones given that matches 77, and therefore all of them will be given a 0, and the summation will be that, and therefore the test fails. So range proof. Oh, so I think I was muted for quite some time. I think when I began looking at range proofs is when I was muted. So we can go back. Just think I began when I was explaining this. Now this is easier. I've already said. Your country secret value is 99. 99 here matches it. This 99 also matches. So this will be true, which you convert to fill becomes 1. This will be true and again convert becomes 1. This is not true, it's false. This is another false. So when you convert false becomes 0. When you sum this, you get it 2. So this summation is not equal to 0. So if it's not equal to 0, then the test passes. So that is what I explained at that point. Let me take away. I also explained that this circuit enforces membership. It does not prove uniqueness. It does not prove index-specific selection, and it will work correctly when there is at least one match. So if there is one match, it passes, the test passes. Or if there is more than one match, the test will still pass. But where there is no match, the test will fail. The test will fail. Then now I was looking at the range proofs, and I was saying that range proofs are useful when a system needs to verify that a given value meets threshold, but does not want to reveal what the actual value is. So for instance, you want to prove that you are between at least 18 years, so age. So you don't want to reveal your exact age, but you want just to tell us, for instance, you're between 18 and 60 inclusive. So range proofs would then fit in that scenario very well. Or you may want to prove that we are below 18 years. So again, range proof comes in. And this is just a scenario where we can apply range proofs. There are several other scenarios that we can apply it. So I wanted to share the code for the range proof. We'll look at it. Just going back, same place. So this was the set membership, but now the range proof is here. So let me just copy this. Okay, the code is here. The code for the range proof is here. I just want to restart my terminal. Oh, sorry. Range. Then we want to enter circuits. Okay, so the proof is here. I began with the strut edge field, which will be a field, the private input. You can see there's no public, but now the range. Okay, we want to verify that we give the mean edge, that you want to show that you at least this edge, at least. So the minimum edge, we make it public, but we don't want to reveal your exact edge. So I decided to give it a help function. Proves x fits in 8 bits, i.e. is between 0 and 256. Those are 8 bits. Now, this is not the main function. The main function will be here. This is just a proof of a help function, just to help me do what I want to do. But now, let's come to the main function. We want to prove that you are at least some edge. So let the difference be the input edge minus the input minimum edge. And then let the maximum be 120. Let edge difference be maximum difference, the maximum edge minus the input edge. Constraints. You constrain this. Now, so this is a circuit. So you may want to run it. I also want to, now I've not included tests. If you want, you can include tests and then run other tests. I've also not included Nago proof, the proof atomic. I've not included it, but for that one, it's easy. Just you would say Nago check. Nago check. When you do Nago check, okay, it says there's another prover. There's another prover atomic. So it's asking if we can overwrite it. Let me see where it is. Oh, it was here, but it's not for this circuit. Let's just delete it. Let's delete it. Then say Nago check. Now, when you do Nago check, there's a prove atomic. So it means you will want to insert your minimum edge. Now your edge, let me say you are 35, and the minimum edge you want it to be 18 or even 16, and this one is not important. You can delete it. So when you do Nago check, no, Nago execute, oh, it says failed argument, but none was, okay. We given exact values when it required an argument. So that means we have to do it again. That means there's something I deleted here. It means I return it. Let's now see. Now go execute. That is what was causing it. I deleted it. Some program will do not use it, as I thought in this case it will not be useful. So when I deleted it, it said it wanted an argument. So now go execute, and it accepts that runs and is successful. It says that we have a witness which has been saved at a target set membership proof.gz. So you just come to where the target set membership. Now, so if you give a wrong value, let's try and give your age to be 14, and the minimum age be 16, and see what we get. Now, so that means that the proof is not fails, because you wanted to prove that you're above 16, but the age you provided is less than 16. So it means the proof is not valid. But if we change this to be 11 and now try to run, it will be successful because above 11. Now go execute. Now execute, and we have this. That is correct. So it's correctly done. The proof passes. Now, so this kind of proofs we can generate contracts with them. So you can want to generate a contract that is a solidity verifier. You may want to proceed, and this I had shown you how to generate solidity verifier earlier, and you can still do that using the same process. That means you may want to come up with another folder called JS that will have generate proof .tl. I want to have another folder of contracts that will have verifier and so on. And I'd already shown you how to do that. So any of these examples I've shown you can be expanded to that direction. So the range proof, you can expand it in that direction. The set membership proof can also be expanded in that direction. Now back to this set membership. Again, let's look what the proof at Tomil, and the 42 was part of that. Let's this time let it not be there. And let us run it and see what we get. So I just want to copy this. Now when 42 was part of that, so it passed. Let's just do CD, come out of circuits, then CD, come out of range proof. I'll get inside set membership, get inside set membership, then get inside circuits, get inside circuits. Okay, let's do now go execute. Then it fails. It fails because the sum is 0 plus 0 plus 0 plus 0, which is 0. So it's just telling you that the country, the secret 42 is not part of this list. Is not part of this list. It does not satisfy this, because this one means that the sum should not be equal to 0. So if the sum is not equal to 0, then it means that your country is one of the listed countries. But if your sum equals to 0, then your country is not part of those listed. So in this case, so 0 is equals to 0. So it means this assertion fails, because the assertion is supposed to be the value here should not be equal to the value here. But now it's not true that 0 is not equal to 0. It's not true. It's not true that 0 is not equal to 0. So in that case, this one fails. Okay, let's try. Let's make this 42 and see. Now go execute. It process. Let's make this one 42 again. Now go execute. It process. Let's make this one 42 again. Now go execute. Good. So this is just 0 plus 0 plus 1 plus 1 plus 1. That totals to 3. And 3 is not equal to 0. So it means this one passes. This one passes. That is why it passed. Okay, let's put values that are not 42. 5, 84, 3 or 5. Now go execute, and it fails. It fails. You see, this is not, though it's a double of this, but it's not this. So we're just matching this and checking whether it equals to that. In cases where it's not equal, the value assigned is 0. So in this case, we have 0, you have 0, you have 0, another 0, another 0, then totaling zeros, you have 0. And so it's not true. It's not true that 0 is not equal to 0. At this point, it's not true that 0 is not equal to 0. And therefore, this assertion fails. So that is why at this point, it fails. So I hope you understood what this set membership, how it works, because in our next lesson, I'll be looking at range proof in detail, and then look what password proofs in detail. Today, I think we've looked at set membership in. Now, again, I emphasize how we write proofs that should fail in Noir. You write should fail here so that when you run it, it does not give you an error. You don't write it like in other languages they do. They write and then use this backslash to omit what will fail so that it doesn't fail. So now you don't do that. Just use the word should fail, and then it passes. It passes without panic. But if your omit should fail, then it will panic. It panics and then it fails. Good. So I think that is what I wanted to cover today, so that in our next class, we'll look at the other two in details. Thank you.